friends, I welcome you all on India's largest live e-learning educational platform, that is Gradeup. Friends, today we are going to discuss one another important topic of your subject electrical machines, that is effect of salient poles in case of synchronous machine. I can tell you that this is one of the most misunderstood and most difficult topic for most of the students. So please have patience. We will be going through this session and we will try to understand what is the effect of salient poles. I hope it is clear to all of you. Good evening, Santosh Kumar. All the candidates who are joining me, please tell me whether my audio and visual quality is okay for you so that we can quickly proceed for the session. Hi Gunda Kavya, how are you beta? All the people who are joining me, quickly tell me whether my audio and visual quality is okay for you so that we can proceed for the session. Till then, some of you may be joining me for the first time, so there is my brief introduction. My name is Ashutosh Saxena, as you can see on your screen. I have 10 plus years of teaching experience in this field. I completed my M.Tech from IIT B.H.U in 2010. I have written a couple of books also on engineering ethics and power system. One of the book for engineering ethics is already in market. My areas of expertise are power system, electrical machines, electromagnetic field theory, material science and engineering ethics. Venkatesh, let me tell you that if you go to the Gradeup app, you will find all things in a comprehensive manner. You will get daily updates, you will get daily schedules, daily sessions, you will get daily quizzes. Lot of things are there if you switch to the Gradeup app. Okay, Supriya, now let us proceed for the session. The next slide on your screen shows the Target GATE 2021 batch. See, because of overwhelming response from our students for the batch 1 for Target GATE 2021 course for electrical engineering, we have started admissions for the second batch. All of you who are interested, listen to me properly. Rakesh Talreja Sir, MEIC Bangalore, AIR 9, 10 plus years of experience. Myself Ashutosh Saxena, M.Tech, IIT B.H.U, 10 plus years of experience. M.N. Ramesh Sir, MU Osmania University, Hyderabad, 17 plus years of experience. Vijay Bansal Sir, 19 plus years of experience. Chandan Jha Sir, M.Tech, NIT Hamirpur, 9 plus years of experience. So very eminent faculties are going to take classes in this batch. If you are interested, if you are targeting the GATE, let me tell you, this is the course for you. The most important feature is it is going to be both in Hindi and English as per your convenient language. And let me tell you that more than 11,000 people have started the free trial. So if you are interested, you can go and you can see how Gradeup is changing the life of thousands of students. Now the next slide on your screen shows the characteristics or the features of this Target GATE 2021 batch 2. You can see there is 550 hours of live classes, very comprehensive classes. 5,000 plus practice questions, study notes covering each chapter and subject in detail, full length mock test for GATE 2021 and daily test and subject wise test for GATE 2021. I am fine, Bhupendra beta, how are you? And let me tell you, the most important thing is the regular classes are going to start from 12th of May. And if you have any query regarding any issue, then you can contact this number or you can contact our backend team member Anand Pandey. You can write email to him directly and he is going to help you in this regard. I hope it is clear to all of you. Now beta, we will be covering one remaining portion from the yesterday class. We have discussed the power angle characteristics of the cylindrical rotor. We have taken the generator case yesterday. Now we are going to take the motor case. Generator we have taken, so now we are going to take for the motor. That is the synchronous motor. Is it okay all of you? Please tell me. Now you please try to see if you are having a motor, synchronous motor. So this is going to be something like this. you are going to apply some terminal voltage from supply to this motor. If this is a motor, this is going to be JXS and this is going to be RA, and this you are calling as Z as angle theta S. And you are going to draw current from the supply, so the current direction is going to be like this. Purushottam saying, beta, this is not the first class. Let me tell you, every class I am saying this, that if you want to study electrical machines and you want this subject to be interesting, if you want to take interest in this subject, then you can go to the Gradeup GATE channel. In the startup series for electrical engineering, we are running these electrical machines classes. This is almost 17th lecture for you, so you can go and you can enjoy learning. Now let me tell you, if you want to know this current, armature current, how can you write this armature current? Suppose this is going to be EF minus del and this is going to be V angle 0. Now the current is flowing from this voltage terminal to this motor terminals. So it is going to be how much? It is going to be V angle 0 minus EF angle minus del divided by ZS angle theta S. Yes or no? Now if you see, you can write IA as V upon ZS angle minus theta S minus EF upon ZS, and this angle is going to be minus of del plus theta S. Now if I ask you, what is the developed power? So developed power is going to be here across the machine. So you are going to write the developed power as real developed power plus reactive developed power. Yes or no? Now this developed power, beta, you can write as EF angle minus del, and what is the current? The current complex conjugate. This is how we are going to write the current. See, Raj Mangal Singh, beta, definitely for SSC JEE also we are coming up, we will be coming up with some fresh batches. Don't worry, just stay tuned to Gradeup. We will be telling you the exact dates and schedule when we are going to start SSC JEE subjects or the batches. Now beta, if you want to know the developed power, you just put the value of the armature current. So it is going to be IF angle minus del, and if you put the complex conjugate of the current, then it is going to be how much? It is going to be V upon ZS. If I have to write the complex conjugate of the current, so it is going to be how much? This angle is going to be plus and this angle is going to be plus. So we can write V upon ZS angle theta S minus EF upon ZS, EF upon ZS. This is going to be angle theta S plus del. Now if you want, then you can simplify this. So beta, you will be getting S developed as VEF upon ZS. This is going to be angle theta S minus del, and this is going to be minus EF square upon ZS, and this is beta going to be angle theta S, because minus del and plus del are going to be cancelled. Now if you want to know what is the real power developed, then you have to just compare the real and imaginary part. So I am writing the real power developed, so it is going to be VEF upon ZS, and this is going to be cos of theta S minus del minus EF square upon ZS, and this is going to be cos theta S. Now if somebody asks you, what is the condition for maximum value of the developed power? So it is going to be what? It is going to be steady state stability limit. You must have read this thing in power system. If not, then you please try to understand. Steady state stability limit will be given by the maximum developed power condition. You remember this curve? This is real power, this is del angle, and this value del is equal to 90 when we were getting the P max. This we were calling as the steady state stability limit condition. Is it clear to all of you? Now if you want to know what is the maximum power developed condition for this synchronous motor, you tell me what is going to be the maximum developed power condition. V, EF, ZF, ZS and theta S you cannot change, because theta S is the, once you design the motor you cannot change theta S, because theta S is the impedance angle, you can say synchronous impedance angle. Terminal voltage, induced EMF and ZS also you cannot change. So what you are going to change? You are going to change del. So if you want the maximum value of this quantity, then you have to make this cos term as 1. So when this is going to be 1, when theta S minus del is going to be 0, or better you can say del is equal to theta S. So this is very, very important conclusion we have seen for the generator case, and you can note it down for the motor case. So whenever he is asking the steady state stability limit for the synchronous generator or motor, then always you are going to find, let me write it here, the steady state stability limit is always found from maximum developed real power condition. Is it clear to all of you? And if you have any doubt, then you can ask me. Good evening, Sai Kumar, how are you? Similarly, beta, you can write for the input power also. What is input power, you tell me? Because you are using a motor, so this is going to be the input power, real and reactive power, which we are calling as input power. And this is going to be the developed power. So can you write an expression for the input power? Yes. What is going to be the input power? You tell me. Input power expression, beta, you can write as input power. We are going to write as S in the voltage and the current complex conjugate. So what is the voltage here? The voltage here is going to be V angle 0, and what is the current? IA. So we are going to take the complex conjugate of the current. So this is going to be V angle 0, and we are going to use the current complex conjugate. If you better solve this, I am writing the final expression. You can just confirm it on your own, because we have done the similar thing. So you will be getting the expression as V square upon ZS cos theta S minus VEF upon ZS. Sorry, this is for real power. Let me write the S expression first. So this is going to be V square upon ZS, and this is going to be angle theta S minus VEF upon ZS. Angle is going to be theta S plus del. You can note down this expression and you can later on compare it with your calculation. So if again you want to know what is the real power, you can write it by comparing the real and imaginary parts. So this is going to be VEF upon ZS cos of theta S plus del. I hope it is clear to all of you. Yes, KCET, how are you? Is it clear, beta? Whatever we have discussed till now, is it clear to all of you? Please tell me quickly. Sai Kumar, beta, I can understand your problem. You better contact the concerned person on the Gradeup app. I think they are going to help you in this regard. Now, beta, we are going to discuss whether it is synchronous generator or synchronous motor. What is going to be the case of reactive power? Let me tell you, this is very, very important concept, and you should not miss this concept, because lot of interviews they are going to ask you about this reactive power, different cases for the synchronous generator and synchronous motor. So first, beta, we are going to take the case of synchronous generator. First we are going to take the case of synchronous generator. Yes or no? Now you see from the yesterday class, what was the expression for reactive power? The expression for reactive power I am writing as Q out. Why I am writing as Q out? Because as a generator you are supposed to supply the real and reactive power. This tendency you must understand, because if you understand this tendency of the generator and motor, you will understand. If you are a generator, then you are going to supply the real and reactive power. If you are a motor, then you are going to consume the real and reactive power. So for generator, what is the expression for reactive power Q out we have? It is going to be V upon, if you neglect the armature resistance, I am neglecting beta, so you are getting V upon XS, and this is going to be EF cos del minus V. This is the expression. You compare with the yesterday class. Yesterday class we have seen it. If you put RA is equal to 0, if you put RA is equal to 0 beta, then you are going to get this expression. I hope it is clear to all of you. So your ZS is going to be simply XS angle 90 degree. Is it clear to all of you? We just put these values in that equation and you will get the expression for the reactive power output of the generator. Now I am going to discuss three cases. What is case 1? Case 1 is if EF cos del is equal to V, then we call it as normal excitation. Then we call it as normal excitation, because if this EF cos del is equal to V, then Q out is going to be 0. I hope you are getting this idea. It means beta, your generator is operating at which power factor? Generator is operating at unity power factor. This is very, very important. I hope you are getting this condition. What is the second condition beta? The second condition, case 2 I am discussing. Second condition, suppose EF cos del is greater than V. If EF cos del is greater than V, you put this value in this expression, so Q out is going to be positive. It means Q out is going to be more than 0 or positive. Now when you are a generator and the output power which you are going to supply is positive, it means this much power you are going to supply. So if reactive power output is positive, it means you are going to supply that much reactive power. So beta, in this case we are saying that your generator is overexcited condition. This we are calling as overexcited condition, and your generator supplies lagging reactive power. I hope it is clear to all of you. Generator is going to supply the lagging reactive power. Yes or no? And your generator is operating at lagging power factor. This is very, very important, frequently asked in various examinations. Yes, Subramaniam Suresh, you are right. It's operating lagging power factor in overexcited condition. You are right, beta. Now let us see case 3rd. Case 3rd, beta, we are saying when you are having EF cos del less than terminal voltage V, what is going to happen? Q out is going to be less than 0. Now this is something where you have to put your mind. When you are a generator and the power which you were supposed to supply is negative, it means instead of supplying that power, now you want to consume that power. Negative power output, whether it is real or real or reactive for the generator, it means instead of supplying that power, the generator is now going to consume that much power. It means generator is going to consume the lagging reactive power. This condition beta we call as under excited condition. Is it clear to all of you? Please tell me yes or no in the comment section. Are you getting this idea? And what is the operating power factor? The generator operating power factor is leading. Now you will ask me, sir, why it is leading? Then I will tell you beta, at the end of the day, when you are saying your generator is going to consume reactive power, it means you can say the same thing, it is going to supply the leading reactive power. I hope you are getting this idea. If you are consuming the lagging reactive power, it means you are supplying the leading reactive power. Both the situations are same. For example, if you tell me that, sir, I have given you 2 chocolates. The same thing I can tell you that, beta, no, you have not given me 2 chocolates. I have given you minus 2 chocolates. So both the things are same. I hope it is clear to all of you. Beta, what you want me to repeat, you tell me. Let me just summarize it once again so that you understand it better. I am saying, first step, you write the generator reactive power output expression. This we have achieved yesterday. Now we are going to compare the relation between EF cos del and V. Case 1, if EF cos del is equal to V, it is going to be normal excitation case. Q out is going to be 0. Q out 0, it means your generator is going to operate at unity power factor. I hope it is clear. Second case, EF cos del is more than V. When beta EF cos del is more than V, then what is going to happen? Q out is going to be positive. When beta Q out is going to be positive, it means your generator is going to supply the lagging reactive power. If you are a generator and you are supplying positive power, then you are a generator. Yes or no? So your generator is operating at lagging power factor because you are supplying lagging current beta. Now come to the third case. Third case, when EF cos del is less than V, Q out is going to be negative beta. Q out negative, you put your mind here, focus here, all of you. If you are a generator and your output power is negative, it means instead of supplying that power, you are receiving or consuming that power. That is the idea. So beta, your generator in this case is consuming the lagging reactive power, so it is going to be under excited condition. And in this condition, your generator operating power factor is leading. I hope it must be clear to all of you. Santi Raju beta, that demagnetizing, magnetizing, then that we will cover when we will discuss the armature reaction. Don't go there. Just listen to me with this equation that we are discussing. Is it okay for all of you? Now beta, we are going to write for the synchronous motor. Now for the synchronous motor, instead of writing Q out, I am writing Q in. Because now your motor is going to consume power. As a motor, you are supposed to consume power. So I am writing Q in. What is the expression for Q in? You can see it beta, it is going to be V upon XS, V minus EF cos del. I hope it is clear to all of you. So this is the expression for Q in case of synchronous motor. Again beta, I am going to take different cases. Case number 1, V is equal to EF cos del. When V is equal to EF cos del, Q in is beta going to be 0. Again it is normal excitation. And your motor is going to operate at unity power factor. I hope it is clear to all of you. Second case beta I am going to take. Second case beta I am going to take. EF cos del more than V. When EF cos del is more than V, then beta this Q in is going to be negative. Yes or no? If this quantity is more than this quantity, so this Q in is going to be negative. Now you again focus here beta. If your input reactive power is going to be negative or less than 0 for a motor, it means instead of consuming that reactive power, now it is going to supply that reactive power. I hope you are getting this idea. When Q in is going to be negative for a motor, then your motor is not going to consume that power. Actually, your motor is going to supply that much reactive power. So, beta, your motor supplies lagging reactive power, and this beta we call as overexcited condition. I hope it is clear to all of you. Yes or no? And what is the operating power factor? The operating power factor, because we are writing it for the motor, so at the end of the day, the motor is going to take current, yes or no? Operating power factor is leading. Is it clear to all of you? Please tell me yes or no in the comment section. Third case beta I am going to take. Third case beta I am going to take. If EF cos del is less than V, if EF cos del is less than V, then your input reactive power for the motor is going to be positive. If your input reactive power for the motor is going to be positive, it means your motor is going to consume that much reactive power. So beta, your motor is going to consume lagging reactive power. This beta we call as under excited condition. And what is the operating power factor beta? The operating power factor is going to be lagging. All of you please tell me, are you getting this idea? Because this is something, if you go to the UPSC or you go to any IIT, they are definitely going to ask you question on this if you are an electrical engineer. And if you can write these two equations for the generator and motor and you can discuss all the three cases, you are going to get full marks in your interview. Is it clear to all of you? Please tell me yes or no. Okay beta. Now beta, we are going to discuss a very important point, that is the effect of change in excitation at constant kilowatt output. I am writing it here. We are going to discuss the effect of change in excitation at constant kilowatt output. Now just see what we are going to do here. It is going to be very important for you to understand beta. When we are saying constant kilowatt output, what is the meaning of this? What is the meaning of kilowatt? Whenever you are talking in terms of kilowatt, you are talking in terms of real power. So beta, simply we are saying P is going to be constant. When beta P is going to be constant, you know P you can write as VI A cos phi. Yes or no? Now if P is constant beta, if P is constant, then you can write IA cos phi is equal to constant. If your voltage is going to be constant, then you can write, if your power, real power and voltage is going to be constant, then you can write IA cos phi is equal to constant. Second beta, you can write your power as VEF upon XS sin del. You remember this formula or not? Very simple formula. When you are saying P is constant beta and V is also constant, then you can say EF sin del is going to be constant. So these are the two conditions which you have to keep in mind when you are going to draw the variation in the excitation and you want to see the different changes. Now beta, I am going to use these two equations and I am going to draw the phasor diagram for the generator. And let me remind you, this beta we are doing for the cylindrical rotor. You don't forget that. First thing is, suppose this is your terminal voltage. Suppose this is your terminal voltage. Okay, this is your terminal voltage. Now first beta we are taking the armature current to be lagging. We are taking armature current to be lagging. Suppose this is your armature current. Okay, so this is going to be your armature current. Suppose this is IA1. This angle beta we are calling as phi 1, and this is your terminal voltage V. Is it clear to all of you? Listen to me properly. Ajit Kumar beta, yes, you can ask your question. What is your doubt? You can ask your question beta. First you listen to me. Let me first draw this, then I will answer your doubt beta. Listen to me. First condition, I am taking the current as lagging. When you are having a lagging current beta, this I am saying IA1. This I am saying as IA1 with an angle phi 1. Yes or no? Now if you want to draw the phasor, what is going to be your excitation EMF? The excitation EMF is going to be resistive drop and reactive drop. Yes or no? Suppose we are ignoring the armature resistance. Suppose RA is 0. So if you want to draw, if you want to add the excitation J axis drop here, so it is going to be 90 degree to this. So you just extend this IA like this, and this 90 degree beta you can draw as like this. So this is going to be JIA1XS. Yes or no? Now what is going to be your excitation EMF beta? Your excitation EMF is going to be something like this. This beta we are calling as EF1. Are you getting this? And this angle beta we are calling as del 1. This is the case when your armature current was lagging. Is it clear? Now I am going to take a unity power factor current. Unity power factor current, but you have to take that condition that IA cos phi must be constant. Yes or no? So it is going to be how much? Suppose this is your IA2. Second case, you are taking the unity power factor condition. So your armature current is going to be like this, in line with this terminal voltage V. Now what is going to be your JIA2 axis drop? What is going to be your JIA axis drop beta? It is going to be something like this. This is going to be your JIA2XS. And beta, what is going to be your excitation EMF? This is going to be something like this. This beta we are calling as EF2. Yes or no? Now beta we are going to take the leading case. Now beta we are going to take the leading case. Suppose leading power factor is there. So we are going to take IA3. But you have to take this condition IA cos phi is equal to constant. Yes beta, you are right PK. So beta, if it is going to be, beta going to be leading current, so this leading current is going to be something like this. Leading current is going to be something like this. But you have to keep this condition intact, that is IA cos phi must be constant. Yes or no? Now if this is your armature current, I am calling it as IA3. What is going to be your JIA3 axis drop? It is beta going to be, something like this. 90 degree to this current, yes or no? So beta, this is going to be your JIA3XS drop. And beta, what is going to be your finally excitation EMF, it is going to be something like this. Okay, let me draw it again. It is going to be something like this. This is going to be your EF3. Now you listen to me very carefully, very important. Yes, beta. Now you listen to me, very important thing we are going to understand here. This line, beta, this line gives you the locus of, this line beta we are calling as locus of EF. Whatever your case, whether it is lagging case, unity power factor case or leading case, your EF locus is always going to be on this line. So beta, this we are calling as permanent residence of EF. You may be living anywhere, but this is your permanent address. I hope it is clear to all of you. And what is the locus of IA? What is the locus of IA, beta? You see here, this is going to be the locus of IA. This is beta we are calling as locus of IA. Is it clear to all of you? Now we are going to make a very important conclusion. What is that conclusion, beta? You see here, this beta angle we are calling as del 1, this angle we are calling as del 2, and this angle beta we are calling as del 3. It means if your power factor is lagging, and suppose your angle is del 1, for unity power factor it is del 2, and for leading power factor it is del 3, then beta you can write the relation as del 3 is going to be more than del 2 is going to be more than del 1. Is it clear to all of you? You can see from this diagram. Now Anik Mitra is asking, sir, leading current will lead the excitation EMF and terminal voltage both are only terminal voltage. Now Anik Mitra, I am going to give you very important point for your notebook. All of you, if you are interested, you can note it down. Whenever for any device, any machine, you are going to write the power factor, whether it is leading, lagging or unity power factor, you will always write in terms of terminal voltage until and unless it is mentioned. Suppose if you are writing the lagging or leading with respect to the excitation EMF, then it is going to be internal power factor, not the real power factor, let me tell you. Because if your machine is in front of you, then you can only see the terminal. You cannot go into the machine, inside the machine, and you can check what is the power factor. I hope it is clear to all of you, beta. Anik Mitra, your doubt is solved or not? Please tell me. Now, beta, similar thing you can do for the motor also. This I am giving you as an exercise. You draw this same diagram for the motor. Is it clear to all of you? You draw this same diagram for the motor, and if you are not able to draw it, then I am going to discuss it in the next class. Is it clear to all of you? Now, beta, we are going to discuss our today's topic that is very, very important. We are going to discuss what is salient pole. I hope it is clear to all of you. Now, all of you just focus here, listen to me properly. It is going to be very, very important. You listen to me properly. If you see, when you are having a cylindrical rotor, for your synchronous machine, the air gap was constant. Yes or no? The air gap was constant. When the air gap was constant, then you can have the effect of armature reaction was easily modeled as XAR. Yes or no? What we have done? We have modeled the armature reaction effect with the help of a reactance, and that reactance beta we are calling as XAR when we were discussing about the cylindrical rotor. One beta, when you come to the salient pole rotor, what is salient pole? Your salient pole rotor is going to be something like this. I am going to just draw it here so that you understand if anybody is not clear with that, and then I am going to just remove that. Is it clear to all of you? So beta, what is going to happen if you are going to have a salient pole? So the situation is going to be something like this. It is going to be something like this. This is going to be your salient pole rotor synchronous machine. So it is going to have 4 poles. Yes or no? You remember this? This is north, this is south, this is north, this is south. Alternate north and south. Is it clear? Now when you are having this beta, we are calling as salient pole. Now you see, if you see the salient pole, the most important difference you see that if you see the air gap is not constant. If you see, suppose this is your direct axis. Suppose this is your direct axis. Okay. And suppose this is your quadrature axis. This is going to be your quadrature axis. Suppose this is your D axis and this is your quadrature axis. So very easily you can say that the direct axis air gap is going to be very less. Air gap is less, minimum. And if you come to the quadrature axis, the air gap is going to be very large. Yes beta, yes Suresh beta. So what is the point I want to make here beta is that if you are going for a salient pole rotor, the air gap is not going to be constant. If beta air gap is not constant, what is going to be? Air gap is minimum along the D axis and air gap is maximum along the Q axis. Now what is happening? If you see, the effect of armature reaction is going to be different along the D axis and Q axis. So for the D axis, because the air gap is minimum, so beta armature reaction effect is going to be more. And for the air gap maximum condition along the Q axis, the air gap is going to be, the armature reaction is going to be minimum. It means if you want to model the armature reaction effect in case of salient pole machine, you cannot use a single value for the equivalent modeled reactance, that is XAR. XAR is not going to help you. So what beta you are going to do? Instead of using XAR, now with this 2 reaction theory for the salient pole as given by Blondel has given a 2 reactance or 2 reaction theory where you are going to use 2 reactances to represent the direct axis and quadrature axis armature reaction effect in the salient pole machine. So what beta we are going to write here? Very important point. You please write it here. It is very important. What is the Blondel's theory? What is Blondel's 2 reaction theory? He said beta, in order to model the armature reaction effect in case of salient pole machine, two reactances are used. Yes, is it clear to all of you? Please tell me. Is it clear to all of you why we are using this two reaction theory? What is the reason? The reason is because of the non-uniformity of the air gap. You are having a different armature reaction response, so it is very difficult to model them with one reactance, so we are using two reactances. Is it clear to all of you? Now I am coming back to the original diagram, and please try to understand here. Now in this diagram, this is a salient pole and there are two poles. It is a two pole rotor. This axis along the rotor we are calling as D axis, and beta this axis which is 90 degree to this D axis, this we are calling as Q axis, and we have used only one phase coil, that is AA dash. Now if you apply the right hand rule, A conductor current coming outside and A dash conductor current coming into the coil. So right hand rule if you apply, then you can find the axis of coil AA dash or phase A dash. Is it clear to all of you? Now beta, what we are going to do, you please try to understand. If this is your, what is this FAR? This FAR is the MMF, or you can say the equivalent MMF, which represents the armature reaction. Yes or no? This FAR is the equivalent MMF which represents the armature reaction. So what we are going to do, we are going to divide this armature reaction equivalent MMF into two parts. One part along the direct axis, that beta we are calling as direct axis equivalent MMF for the armature reaction, that is FD, and one beta we are putting in the direction of this Q axis, that beta we are calling as FQ. I hope you are getting this idea. All of you please tell me, are you getting this or not? This is going to be very important to understand. If you don't understand this concept, then it is going to be very difficult for you to solve the numericals. And let me tell you, once you understand this basic concept of saliency, then the questions are going to be very easy for you in the GATE examination, and very easily you can solve the numericals. You have to just put the values if you know this basic background and theory. Is it clear to all of you? Now beta, again I am repeating, I am saying that I am just writing it here so that you can note it down. What we are going to do, the FAR, that is the equivalent armature reaction MMF, it is divided into two parts, okay, FD and FQ. FD along the D axis and FQ along the Q axis. I will tell you the exact diagram, you just focus on my words, what I am saying. I am saying that armature reaction equivalent MMF FAR we are going to divide in two parts, that is FD. FD is along the D axis, FQ along the Q axis. Is it clear? Itna clear hai? Agar itna clear hai, then we can proceed. Now beta, you just see this diagram. This diagram is going to be very important and you will understand everything. You just see here. This diagram, if you understand, then rest of the salient pole, all the phasor diagram, everything is going to be very easy for you. Okay, just let it be here. Okay. Now you just focus here, beta. All of you focus here. This we are calling as D axis Yes or no? And this we are calling as Q axis. Now one thing you have to make in your mind very clear, that you are going to represent the armature reaction of FD, and this IQ is in the direction of FQ that we have just discussed. The equivalent MMF of the armature reaction we are dividing into two parts, FD and FQ. Now FD के along you will get ID and FQ के along you will get IQ, and ID से आपको मिलेगा phi D and phi Q मिलेगा IQ से. इतना सबको क्लियर है? Is it clear to all of you? Are you getting this idea? This is very important. If you understand this, then rest thing is going to be very easy for you. Is it clear to all of you? Now one thing you have to remember in your mind. What is that? That is beta, your IQ and EF, they are going to be in phase. That is first point, very important point. IQ, you can see your IQ and excitation EMF, they are in same phase. And ID is going to lag EF by 90 degree. That is very, very important. These two things you have to remember. Is it clear? The moment you understand this, that IQ and EF are going to be in phase and ID is going to lag EF by 90 degree. I know that it is difficult for you to understand this at this point of time, but I am telling you to remember it for the time being. Later on I am going to explain it why we are taking it so. But for the time being it is important that you understand this. IQ component of the armature current is going to be in direction, in phase with the excitation EMF EF, and your direct axis component of the armature current is going to be lagging the EF by 90 degree. Is it clear to all of you? Is it clear to all of you, beta? Now you see, I am going to tell you very, very important point. And if you understand this, you will never ever do mistake in the salient pole numericals, synchronous generator or motor numericals. We are saying that phi q is going to be in the direction of IQ, and IQ is nothing but, see, this MMF is what? Number of turns multiplied by the current. So the quadrature axis component is in direction the quadrature axis armature current. Similarly, this phi d is in the direction of ID and ID is in the direction of FD. Now you please listen to me very properly. Because this flux is going to experience minimum reluctance, and this flux is going to face maximum reluctance because of the pole saliency. You can say minimum reluctance phi d direct axis or maximum permeance. What is permeance? The reciprocal of reluctance. And maximum reluctance or minimum permeance. You are going to be surprised by this idea, beta, that even though phi q, f q, I q are in same direction, phi d, f d and I d are in same direction, but the armature reaction is not in phase with this armature current. This is very important point. All of you should note this down. This is very, very important point. That your armature reaction flux, equivalent flux, is not in phase with the armature current. There is some phase difference. Now you will ask me, sir, why it is the phase difference? Why this armature reaction flux is not in the direction of armature current? The reason is the direct axis is going to have minimum reluctance or maximum permeance, and your quadrature axis is going to have maximum reluctance or minimum permeance. I hope it is clear to all of you. Even though the armature reaction MMF and armature current are going to be in direction, because it is this armature current who has produced this armature reaction MMF, equivalent MMF. but this flux is not going to be same in this direction. Is it clear to all of you? This is very, very important, and if you don't understand this, you are going to do mistakes in the real GATE examination. I hope it is clear to all of you. Can we move now? Now beta, I am going to write the theory part, that is very, very important, and now the only thing is that you understand the mathematical interpretation. Now let us see what is mathematical interpretation. Beta, I am writing this direct axis flux component of the armature reaction as PD into FD. What is this PD beta? This is permeance, the reciprocal of reluctance. You remember this? You remember this equation? We were writing flux as MMF upon reluctance, and this 1 upon reluctance you can write as permeance, so you can write flux as permeance multiplied by MMF. Is it clear to all of you? So if you are having this equation, you can write this for the direct axis flux PD into FD, yes or no? Yes or no? And this beta we are writing as PD, and what is FD? This is the direct axis armature reaction MMF component, and this beta we are writing as KAR into ID. This KAR is some constant, you can say winding constant. And similarly beta, you can write the quadrature axis component as the permeance for the quadrature axis. Now Sankirtan Gaddam is asking, sir, can you practically explain why there is a difference? Let me tell you beta why there is a difference. You listen to my words properly. When you are going for a salient pole machine, the air gap flux, you can say the air gap is going to be different for direct axis and quadrature axis. The reluctance or the permeance value is going to be different. I hope it is clear to all of you. This is the reason. Yes or no? Are you getting this idea or not? See, if reluctance is high, then flux is going to be less. If reluctance is less, the flux is going to be high. So because of this dual nature, the resultant armature reaction flux is not in direction with the armature current. This is the reason. I hope it is clear to all of you. Now beta, you see here, we are writing for the direct axis flux, so it is going to be permeance for the quadrature axis multiplied by this MMF for the quadrature axis component. So this is going to be PQ. What is FQ? This is going to be KAR, some armature reaction constant you can say of the winding, and this is going to be IQ. Is it clear to all of you? This KAR you can say a constant for the armature winding. Is it clear to all of you? Now let us see here what we are going to do. We are writing now this armature reaction, ultimately we are going to model with the help of reactance or in terms of voltage drop. Yes or no? In terms of reactance or voltage drop. So beta, I am writing this voltage drop for the direct axis beta, I am writing as minus J KE, and this is going to be phi D, some constant we are saying, and beta this quadrature axis component I am writing as minus J KE, and this is going to be phi Q. Yes or no? Now I am going to write the resultant EMF. I am going to write the resultant EMF. How I am going to write? Just see here. This ER is going to be the excitation EMF plus ED plus EQ. Yes or no? Because this ED and EQ drops are going to be negative. Because you are not, see, you were supposed to get this. You were supposed to get this. But because of armature reaction, because of this drop, You are not getting EF. What you are getting? You are getting ER. I hope it is clear to all of you, beta. Now we are writing ER, beta, as EF plus, or you can write it with minus sign, beta. So it is going to be how much? It is going to be minus JXE phi D, not XE, it is going to be KE. Phi D minus J KE phi Q. Is it clear to all of you? This equation I am writing, is it clear to all of you so that we can proceed? Is it clear to all of you? Please tell me quickly yes or no in the comment section. Now what I am going to do, beta, I am going to put the value of this phi D and phi Q from this equation. I am going to write the value of phi D and phi Q in this equation. Now see what we are going to do. We are going to write ER as EF minus J KE. What is going to be phi D, beta? Phi D is going to be KE, and this is going to be PD, and this is going to be KAR. Okay, it's okay, beta. And this is going to be ID. And similarly, beta, we are writing for this phi Q as minus J KE, and this is going to be PQ, and this is going to be KR, and this is going to be, beta, IQ. Now I am going to put very important point. All of you listen to me very properly, beta. This quantity, beta, we are calling as X DAR. You focus, that is very important. If you miss this, then you are going to get confused. I am writing this quantity as XDAR, that is the armature reaction direct axis component of the equivalent reactance. And this quantity, beta, we are going to write as XQAR, that is the quadrature axis reactance component of the armature reaction. I hope it is clear to all of you. Now I am going to write it here, beta. All of you just listen to me. We are going to discuss all these phasor diagrams. First you listen to me, beta. So, beta, we are going to write ER is equal to EF minus, and beta, this is going to be minus J XDAR ID minus J XQAR IQ. I hope it is clear to all of you. Now, beta, I am going to write for this ER. Can you tell me what is this ER, beta? Can you tell me what is this ER? For a generator I am asking. Can you tell me what is this ER for a generator? Beta, this is going to be the terminal voltage VT. In terms of phasor summation, I am writing VT plus IARA plus JIAXL. Yes or no? If you remember the phasor diagram for the cylindrical rotor, you will remember this. What is this ER? This ER is going to be, if you remove from EF the armature reaction effect, then you will get ER. But this ER is going to be how much? Terminal voltage, armature reaction drop plus the leakage, equivalent leakage reactance drop. You are modeling the leakage flux by using the leakage reactance drop. So I am going to put this value of ER here. So you are going to get the equation for EF. So beta, you are going to get VT plus IARA plus J. What is this IA? This is going to be, beta, IAXL, and this is going to be plus JXDAR ID plus JXQAR IQ. Subramanian Suresh, beta, you don't worry right now for this value of XE and XAR. These are experimental values. You are never going to be asked about this. Just I have given you this explanation so that you understand how this XAR, XD, XQ has come. Now if you understand today's lecture, nobody can question you in the interview what is this XD and XQ. You can explain this derivation and he will understand. And if somebody asks you the value of this, you just tell him or her that these are experimental values. Now beta, you focus here. What I am going to do, I am going to divide this armature current into two parts, that is ID plus IQ. Are you getting this or not? I am going to divide this armature current into two parts, ID and IQ. See, this is not arithmetic sum, because ID and IQ are at 90-degree phase difference. This is phasor sum. In some books you will find vector sum, but vector is not the right way to write it. It is phasor, not vector. So beta, we are writing this EF. I am writing the final equation. This is going to be VT plus, I am writing it like this. It is going to be IARA plus beta, this is going to be JXD and this is ID. JXD ID plus JXQ IQ. This is the final equation beta which we are having, and this is the way how we have achieved it. Now if somebody asks you what is XD and XQ beta, then you can tell him that beta XD is going to be XL plus XD armature reaction. And what is XQ beta? XQ is going to be XL plus XD armature reaction. Is it clear to all of you? Is it clear to all of you? Please tell me yes or no in the comment section so that I can get your response. Are you comfortable with this? Understanding how this equation we have achieved, and what is the final equation we have achieved for this excitation EMF for the case of generator. See, we are discussing for the generator for all the cases, whether it is for generator or motor, leading case, lagging case, everything we will take from this only. You just understand that it is going to be for the generator. For the rest of the cases we can easily change the sign and we can get the values beta. So it is going to be beta VT plus IARA plus beta, it is going to be JXDID plus JXQIQ. This is the final expression that we are getting. Is it clear to all of you? Are you comfortable with this? Okay. Now beta, I am going to one phasor diagram that is very simple and you can very easily understand this. Now you just focus here. If you understand this phasor diagram, then further phasor diagram you will easily understand. One thing you have to maintain, what is that? IQ is going to be in phase with EF and ID is going to be lags EF by 90 degree. These 2 points if you remember, then you will easily draw the phasor diagram. Okay beta, I will correct it. If I have written it wrong, then I will correct it. I have written it correct beta, what is the problem? Okay, here I have written it wrong, no problem. I hope it is clear beta. Actually I wanted to check whether you are seriously listening to me or not. That is why I just wrote it wrongly. Is it clear? Is it clear beta? So I will just make you understand this phasor diagram, and the rest two diagrams we are going to discuss in the next class, then only you will understand. Now you focus here. 2 points you just understand. IQ is going to be in phase with EF and ID is going to be lagging the EF by 90 degrees. This we are saying for the generator case. These two conditions we are saying for the generator case and lagging power factor condition. I hope it is clear to all of you beta. Now you focus here. The first thing what you do beta, first thing you draw this line for EF. First you draw this EF. Is it clear? The first thing that you are going to draw is EF. I am going to tell you the steps how you are going to write it. First you draw this EF. Now I have told you that IQ is going to be in phase with EF. So beta you draw this this is going to be IQ. This beta we are drawing as IQ in phase. This beta we are writing as IQ in phase. This is IQ in phase with EF. And I told you that ID is going to lag the EF by 90 degree. So just 90 degree lagging beta you draw this ID. This is going to be your ID. This is beta your ID, which is lagging this by 90 degree. Is it clear to all of you? Yes or no? Now if you are a generator, then you will start from the terminal voltage and you will reach to the excitation EMF. Yes or no? If you are a generator, then EF is going to be more, terminal voltage is going to be less. So you are going to start from the terminal voltage, you will keep on adding the different drops and you will reach to the excitation EMF. So I am starting with this terminal voltage, VT. Is it clear to all of you? I am starting with this terminal voltage VT. This is beta terminal voltage VT. And because we are taking a lagging case, so the armature current is going to lag this terminal voltage by phi. So first angle we are making phi angle, which is in between the terminal voltage and armature current. This is important point, you should remember this. Now you add the armature resistance drop IARA. Remember that equation that we have just derived. Now beta this armature resistance drop is going to be in the direction of armature current because it is resistive drop. So you just draw this IARA in parallel with this. You draw this IARA drop parallel with this armature current. Yes or no? Now you are going to add the XD and XQ drop. Now XD drop is going to be with the ID current. What is ID current? This is ID current. And this is going to be J times ID XD. So J times ID XD is going to be 90 degree ahead. So beta this is going to be your ID XD drop. And this is going to be your IQ XQ drop because this is your IQ. I hope now this phasor diagram must be clear to you. Now there are three angles which are important. One angle is phi angle, that is the power factor angle. Then there is del angle. This del angle is between the excitation EMF, EF and VT. This is the second important angle. This was the first. And the third angle is beta xi. This angle is beta going to be, this xi angle is going to be between the armature current and the excitation EMF. This is going to be in between excitation EMF and the armature current. These three angles you have to remember. Till now, if it is clear beta, then I am going to conclude the today's session, and the rest part of these two phasor diagrams for the generating action and the motor action we are going to discuss in the next class. Till now everything is clear to you, all of you, please tell me quickly, are you comfortable with this? Tell me beta, are you comfortable with this, whatever we have discussed now? The remaining part we are going to discuss tomorrow. If you have any doubt, then you can ask me. One question also we are going to do on this, very interesting question, so that you understand this concept. Now beta, apart from this thing, we are going to take up the power angle characteristics of the salient pole machine on Monday. Tomorrow Saturday there is going to be no class beta, but on Monday we are going to continue from here. You just revise it. On Monday we are directly going to derive the equations from which you are going to solve the numericals for this. So don't forget to join me on Monday. Same time, 8:30 p.m. startup series, electrical machines for electrical engineer, YouTube, Gradeup, GATE channel. Don't forget to join me. And if you have any suggestion, any feedback so that I can improve upon my lectures beta, please put your suggestion or feedback in the comment section so that every student is benefited beta. And don't forget to like this page and share this video with your friends and colleagues. Then only we can be motivated to make on such videos again and again. Is it clear to all of you beta? Now beta, one very important last information for you, that there are 60 plus Gradeup students in the top 100 of the GATE 2020 examination. If you want yourself to be here, then you have to do better two things. Number one is hard work. And what is second thing, you tell me? What is second thing? Number one is hard work. What is second thing? Quickly tell me, all of you. I want all of you to tell me what is the second thing you are going to do if you want your picture to be in this panel. First thing is hard work. What is the second thing? What is the second thing? All of you please tell me quickly. Beta, second thing is going to be again hard work. There is no substitute to hard work beta. There is no substitute to hard work. I hope it is clear to all of you. So friends, thank you so much for joining me in this session. I wish you all the best for your upcoming exams. Don't forget to join me on Monday 8:30 p.m. for this electrical machines. It is going to be very interesting and very informative session for you, and you will be able to solve difficult questions in the salient pole, alternator or motor. Thank you so much for your time beta. Thank you so much.